numbers in the chat box. Okay, so my today's topic is also from module 1 and it goes by the name Chebychev's inequality. Now, this Chebychev's inequality is actually a topic, is a kind of probabilistic inequality which is irrespective of what sort of random variable you use. Your random variable may be discrete, your random variable may be continuous, but a Chebychev's inequality can be used for both of these types of problems. Problems related to continuous random variable, problems related to discrete random variable. Since we have not done the continuous random variable case yet, so I'll be discussing the Chebychev's inequality and its discrete. I shall consider the problems with respect to its discrete case only. And you just pay attention because it is important topic, and you have to understand that why we actually take help of the Chebychev's inequality sometimes. First of all, let me talk about the technicality of the Chebychev's inequality. Okay, let me first of all define what Chebychev's inequality is. If capital X is a random variable, if capital X is a random variable, discrete or continuous, whatever it is, next time when we'll be doing problems of Chebychev's inequality for continuous case, I shall not be writing this part because this inequality I am defining today only. Next time the inequality will not be defined. You have to keep this in mind. So if X is a random variable, discrete or continuous, with mean mu, which we actually denote by expectation of capital X, and variance sigma square, which we denote by V of X. If a random variable is defined in this particular way, then for any positive number, remember this statement is very important. For any positive number, I am underlining this section. Remember, it is not for any number, it is only for positive number k. I am denoting the number by k. We have the following inequality, which is termed as the Chebychev's inequality. What is the inequality? We are supposed to find probability of this quantity, modulus of X minus mu greater than or equal to k times sigma, and this probability will be less than or equal to 1 by k square. Now, what is the meaning of this inequality? What is the motivation of learning this type of inequality? That motivation will be discussed very shortly. But first of all, as I have told you that I'm now discussing the technicality. You have to digest how to write the inequality. So first of all, let me discuss the mathematical technicality of the thing. Okay. Only thing that you have to ensure for yourself is that whatever I'm writing on the board, that you are understanding the mathematical part of it. Okay. Make ensure that you are understanding the mathematical part. So what am I saying? I'm saying that I'm going to calculate a probability of this quantity, and its probability will be found always less than or equal to the quantity which is denoted by 1 by k square. Okay, so what is that? Now, to understand this particular expression, let me talk about something different. Say, for example, we have an event capital A. In general, we have an event capital A. Capital A means this event is happening, and its complementary event is denoted by A bar, that the event is not happening. You know this very well. And you also know that probability of A bar is equal to 1 minus PA from axiomatic viewpoint. Okay. So this is my prerequisite number 1. To understand the meaning of the Chebychev inequality, this is I'm considering as a prerequisite. This is the prerequisite number 1. My prerequisite number 2 is the following. Prerequisite number 2. Suppose we have a real number, x is a real number. X is a real number. Okay, and we know from real analysis that if we take the modulus of this particular real number, because you know that mod x is a function. So if I take this modulus, if I operate this function on the real number, and if I write it in the following manner, that mod x is less than a or less than or equal to a, I'm not bothered about equality sign, it can be put anywhere. So less than a, then it implies, and implied by, it means that x is lying between minus a and plus a. We know these rules from our school days. Okay. So I'm going to apply these two prerequisites over here. I hope that you are now going to understand what do we mean by this quantity. Okay. So suppose, for instance, I'm considering this term that I have marked over here, mod of x minus mu greater than or equal to k sigma. I am considering this entire quantity as event. I am denoting that this is an event. Okay, I'm considering that this is my A. If this is your A, then your complementary event will definitely be mod of x minus mu less than k sigma, just the opposite, where equality sign will not be there because equality has been included in the event capital A. If you do not understand any part, and if you want me to repeat some part, then you can ping me by writing in the chat box. Okay, otherwise you just I'm carrying on. So if I'm denoting this particular expression, mod of x minus mu less greater than or equal to k sigma, by the event capital A, then its corresponding complementary event will be mod of x minus mu less than k sigma, which will be denoted by the complementary event A bar. And we know that probability of A bar is equal to 1 minus PA. So let us try to calculate the probability of A bar over here, and let's try to find out what comes. So probability of A bar in this case will be nothing but the probability of this quantity, mod of x minus mu less than k sigma. Okay, because this is my A bar, and probability of A bar is actually means probability of 1 minus probability of A. Now I am going to substitute the expression for A that I have considered over here. So it is 1 minus probability of this quantity, mod of x minus mu greater than or equal to k sigma. This is my A, and from this I can actually write the following. I can write probability of mod of x minus mu greater than or equal to k sigma. I can write it as 1 minus probability of mod of x minus mu less than k sigma. It is pretty obvious. I could have written it directly, but since there are so many expressions, mathematical notations, so you may face some sort of difficulties. So I am just showing you this in an explicit sense so that you shouldn't face any trouble. I hope that you are not facing any trouble. So we have got this expression and this expression. We do not have any problem with that. But from the above inequality, we know that this quantity, probability of mod of x minus mu greater than or equal to k sigma, this quantity is actually less than or equal to 1 by k square. If this is less than or equal to 1 by k square, and this quantity is equal to 1 minus probability of mod of x minus mu less than k sigma, so this entire quantity will be less than or equal to 1 by k square. And from there, we can take the quantities on some quantities on the left hand side and some quantities on the right hand side by interchanging the quantities, the sides of the quantities. We can get ultimately from this we are going to get ultimately this expression, that probability of mod of x minus mu less than k sigma this is going to be greater than or equal to 1 minus 1 by k square. Okay, so I am giving this as equation number 1 and inequation number 1, and I'm giving this as inequation number 2. Now I'm going to moving on to the next page, and I'm going to write both the two inequations that I have obtained over here. I'm going to write it in the next page once again, and then I'm going to analyze that what have we got from this particular analysis. So we have got two expressions. One expression is the following: that probability of mod of x minus mu greater than or equal to k sigma. This is less than or equal to 1 by k square. And number two expression that we have got is the following: probability of mod of x minus mu less than k sigma is greater than or equal to 1 minus 1 by k square. Both of these inequalities are actually termed as Chebychev's inequality. Both inequalities are equivalent. One inequality can be derived from the other. Okay. So these expressions, these are the two expressions that we will be often using in solving problems. Now let me analyze that what we mean by this quantity. What we mean by this. If I try to keep the Chebychev's inequality in this form, you will not be able to understand the meaning, the actual meaning in its entirety. So I am not considering this particular form right now. Rather, I am interested in analyzing this form. So let me analyze this form. If you can analyze the form 2, then you'll automatically understand what do we mean by form 1. Okay. Now here comes our prerequisite number 2. My prerequisite number 2 gives us that if x is any variable and mod x is the function which is less than a constant real number, then it is implied and implies the following: that this variable is lying between the negative of the real number and positive of the real number. So it's lying between minus a and plus a. So by applying this rule, we can say that if I treat x minus mu, for instance, if I consider this x minus mu, this quantity to be my small a, so you see that we have got a similar kind of expression over here. And I'm treating no, this is my x, not a. I'm considering mod of x, I'm considering capital X minus mu to be my small x, and I'm considering a to be this expression, that is k sigma. So you will get a similar sort of expression over here, and this implies that this is equal to minus k sigma less than x minus mu by less than k sigma by this rule. And if I'm going to add this quantity mu on all the sides, then we'll be getting this quantity mu minus k sigma x minus mu plus mu plus k sigma, and it is simplified to the following form: mu minus k sigma less than x less than mu plus k sigma. So whenever you are actually trying to find out the probability of this quantity, it actually means that you have the you have the knowledge of the mean of the random variable and some positive number times the variance, and you have this knowledge also, mu plus k sigma. What you are going to do, you are going to calculate the probability that your random variable will fluctuate between this quantity, mu minus k sigma and mu plus k sigma. What is the probability that your random variable will fluctuate? What is the probability that your random variable x will fluctuate between these two numbers, mu minus k sigma and mu plus k sigma? And Chebychev's inequality tells us that this probability will be greater than or equal to 1 minus 1 by k square. So Chebychev's, if you carefully observe, look at Chebychev's inequality. Chebychev's inequality actually giving me a kind of lower limit to the probability. Actually, what happens? Actually, when we are given a probability problem, we are given a random variable. We try to find what is the probability that the random variable takes certain values. and we actually get some value. We put equality sign over here. Usually it happens. But in Chebychev's inequality, what happens? We do not get the exact value. We actually get a range, a kind of range. And not only the range, I shouldn't say it a range, rather it would be a kind of lower limit. We do not have any idea about the upper limit. Actually, we know that if this is my origin 0 and this is my number 1, and we know that probability of any event will fluctuate between 0 and 1. Now, Chebychev's inequality is giving you certain numbers which is greater than or greater than 0, lying here or here or here, and the probability of the event is either equal to that or greater than this. We do not know anything about the upper limit. Upper limit is not given by the Chebychev's limit. Okay, so we actually get this sort of thing from the Chebychev's inequality. Okay, so we can say the probability of some event will be greater than, say, half. Now it means that it can be greater than half. It can be exactly, it can be greater than, it can have any number which is greater than half, but we do not know what is the number. We do not have any idea. So therefore, Chebychev's inequality is the kind of weak inequality to calculate the probability. It doesn't give us the actual value. It only gives us a lower limit. Okay, sometimes the situation may so arise that we are not able to calculate the actual value for the event. Actual value of the probability of the event. It is not possible always to calculate this. So in these cases, Chebychev's inequality can be, we can take the help of the Chebychev's inequality. Okay, so let us try to do a problem with the help of this Chebychev's inequality, and you will understand that what is happening over here. So at this point, if anybody wants to ask me anything, or if anybody has any question, he or she can write in the chat box before I move on to the problem section, that you have understood what is actually we're supposed to find. And if you ask me what is this, it is just the opposite of what we have just discussed. If this gives you, this expression gives you what is the probability that the random variable fluctuates between, suppose diagrammatically, if you want to understand, suppose this is my mu and this is my quantity mu minus k sigma, and suppose this is my quantity mu plus k sigma, then Chebychev's inequality, this form, the second form, gives me what is the probability that your event's probability will lie between this. Okay, so this is what we are going to find. And second one gives you what is the probability that it will be falling in this region or in this region. Okay, so it is all about a region, but only difference is that here actually I'm considering the discrete random variable case only. The same inequality can also be developed in the same way. It can be also understood for continuous random variable also. Okay, so I'm not going to discuss any continuous random variable problem right now because we have not discussed it. Yeah, mu minus k sigma. If mu minus k sigma is is a number. It is a number. It can be greater than 0 or it can be equal to 0. It doesn't matter. You have to mu minus k sigma can be anything. It is a number. We do not have any problem with the number, whether it is positive or negative or 0 or whatever. But if it is, you have to keep in mind that the entire thing should be defined in such a way so that the probability shouldn't exceed its valid limit. It should not be greater less than 0. It should not be greater than 1. Until unless this is till this is satisfied, we do not have any problem about anything. Mu minus k sigma can be 0 also, can be a negative number also, can be a positive number also. It can be anything. So for example, if someone says if you have a random variable x, what is the probability that x will lie between 0 and say 2.5. Suppose. So this is also a valid question. Okay, but you have to ensure that the probability, the value of this quantity should not be less than 0, should not be greater than 1. Numbers can be anything. This number is a real number. It can be anything. Okay, so let's do a problem. Thank you for asking this question. The questions are always welcome. Each time when we teach, we cannot remember each and every point. And so when you ask questions, then we realize that, yeah, this particular point we need to discuss. Otherwise, the discussion remains incomplete. So now I'm giving you this problem. A symmetric die is thrown 600 times. Find the lower bound. Find the lower bound for the probability of getting 80 to 126s. Okay, this is the problem. And whenever we are now going to analyze this particular problem. Okay, so we'll dissect the problem and we'll try to understand that how can we solve it. First of all, if this type of question is given to you, first word that actually I'm attracting me is the word lower bound here. And whenever this word is present, we immediately understand that we have to do the particular problem with a kind of probability tool which has inequality in it. So we can think of Chebychev's inequality. Now, Chebychev's inequality is not the only inequality in probability theory. Other inequalities are also there. Say, for example, Markov inequality is there, and Jensen's inequality is there. Different types of inequalities are there, but these inequalities are beyond the scope of your syllabus, so I'm not discussing it. So whenever sorry, where is this? Just a minute. I think I lost the whiteboard. Okay, so several inequalities are there. So since these inequalities are beyond the scope of our syllabus, so I'm not going to discuss this Markov inequality and Jensen's inequality. But since we have learned Chebychev's inequality, we can only think of Chebychev's inequality. But the important point is that whenever we talk about bounds, upper bound or lower bound, whatever it is, then we can think of any probabilistic tool which is having inequality in it. Okay, so this is the first part that you have to keep in mind. Second part, we have to think about whether the system is biased or unbiased. Okay, so my checking is since lower bound is supposed to be found, think of probability inequalities, probabilistic inequality. I am telling you how to approach to do the given problem. Okay. Once you identify the system, then you can apply the rules. Second checking is it biased system or unbiased system? Is it biased or unbiased? Okay, fine. So if you want to check it, you see that we have this word symmetric die written over here in this particular problem. Since the die is symmetric, so every face has equal chance of being reflected when the die touches the ground. So our conclusion is that the given system is a biased system. Sorry, unbiased system. If the system is unbiased, we have to think about the random variable. What is the random variable? variable here. Now, Random variable is a number you know already, and it gives us a count. So we will denote the random variable by x, and we will say that this x gives us the count of 6. In count of 6. Okay, so this is my random variable. In this way, the random variable has been defined over here. Fine. My fourth part is to identify whether we know the mean of the random variable and variance of the random variable or not. Okay. First of all, we can, okay, let me write it. What is mean of x? Do we know it? And what is the variance of x? Do we know it? These are my questions. To answer these questions, we have to identify the underlying probability distribution that the random variable can follow. Underlying probability distribution that the random variable can follow, that x can follow. Okay. So to identify the random variable, what you need to identify, we need to identify what are the parameters. Do we know the parameters? First of all, since so far we have learned two probability distributions. One is the binomial probability distribution, another is the Poisson probability distribution. Let's think about the binomial probability distribution. In binomial probability distribution, we have n as the number of experiment or number of observation. You see, try to look for it in the question. You see the symmetric die is supposed to be thrown 600 times. So n is your 600. And since it is a symmetric die, and we are interested in finding the 6 on the upper face. So here the success is being defined to be getting 6. And we know for a single throw, the probability of success, which we denote by small p, is equal to 1/6. So you see that we know n and we know p. So the probability distribution has been correctly identified. We can think of, I'm not saying that it would be following, try to understand what am I saying. I'm not saying that x is following the probability distribution, but I'm saying that the x can follow the probability distribution. It can follow, it is valid to follow the probability distribution, which is binomial. Because after doing the experiment many a times, the unbiased thing may become biased, and it can start following some other probability distribution. Right now, we are in a situation that we can assume that it can follow the binomial distribution. And as soon as we know that it is a binomial distribution, we know that what will be the mean of the variable x and what will be the mean of the variable y. We know that the mean of the variable x is np and variance of the variable will be npq. And this is 600 into 1/6, that is 100. And this would be 600 into 1/6 into 5/6, that is 500/6. So we have not started solving the problem. We have dissected the problem in the following manner, and we have found that what sort of probability distribution that we can think of. Now, let us try to find out the lower bound. Okay. We have several forms of the probability inequalities we have come across. And what am I supposed to find? We are supposed to find something of lower bound, something of this sort that we are supposed to find, isn't it? Something of this sort. And we are actually supposed to find that, if I try to write it explicitly, we are actually trying to find that what is the probability that x, the count of 6, will lie between 80 and 120, and it will be bound by certain lower bound. Now you see that, let us try to look at this point, this greater than or equal to inequality. Now you see, go to the Chebychev section. Chebychev section, if you try to, you have got two inequalities so far. So if you try to use this inequality, this form of the inequality, it has less than or equal to type here. So it will not work appropriately, properly. And this inequality has greater than or equal to type here. So it is better for this particular problem if I use form number 2 of the Chebychev's inequality to do the problem. Okay, so in this manner, we can choose which particular form of the inequality that we must select to solve the given problem. By the second form of the Chebychev's inequality, we have the following, that probability of x minus mu less than k sigma, this should be greater than or equal to 1 minus k square. Okay, and we know that this mu is actually the expectation of x, and this k sigma is actually the standard deviation of x. Now variance of x is 500 by 6, so the standard deviation is actually 500 by 6, positive square root of that. So I'm going to write 500 by 6 positive square root of this greater than or equal to 1 minus 1 by k square. Okay, and we know from real analysis that this is nothing but or equals to minus k root over 500 by 6 less than x minus 100, because expectation of x is 100 less than k root over 500 by 6. This should be greater than or equal to 1 minus 1 by k square. And this, if I try to write, add 100 on all sides, we are going to get this quantity on all the sides. But according to the problem, your lower limit is to be 80. That means 100 minus k 500 by 6 root over, this should be equal to 80, and 100 plus k 500 by 6, that should be equal to how much? 120. If I solve this, if you solve this thing, you will find for both the cases, you are going to find that k into root over 500 by 6, this will be 20 for both the case. And consequently, we can take the square. So k square will be equal to 20 by 500 by 6. And this is 20 square. And this would be equal to 400 by 500 multiplied by 6. And that is 24 by 5. So what we have got? We have got the value of k square from this expression. Now your job is to put, if we have k of this value, then we can write here 80 and we can write here 120. And on the right hand side, we are going to put the value of 1 by k square, which is 5 by 24. And thus the lower bound comes out to be x lying between 80 and 120, which is 19 by 24. This is your answer. You are going to, this session is going to end. So please join in the next session. We'll do another problem before we end our today's class. Okay, so I'm stopping here right now.